All right, good morning. So last time we talked about halogenation at the alpha carbon, and so I'm not going to go over that much more today, other than the fact that we can control whether we get overhalogenation or monohalogenation, and what are the two conditions. How can I get acid or base, right? So under acidic conditions, we typically get mono, and if we do it under basic conditions, we get over-alkylation, we get exhaustive alkylation. And if the ketone happens to be a methyl ketone, we actually end up having what's known as the haloform reaction, right? And so we can generate things like chloroform and bromoform and iodoform very, very easily through those reactions, and it allows us to generate carboxylic acids from methyl ketones pretty easily. So we're going to skip the halogenation stuff because we've already covered that. And we're going to go into what we can do with enolates. So one of the very powerful things that you have with an enolate is that it allows you to create a nucleophile that can attack a carbon electrophile. Now that carbon electrophile can be a variety of different things, but for today we're going to talk about alkyl halides. And so if I take a ketone, for example, that has at least one alpha hydrogen on an alpha carbon, I treat this with LDA and THF at minus 78 degrees. I'm going to deprotonate that hydrogen and I'm going to make an enolate. Now under these conditions, what kind of enolate will I get? Excuse me? We'll get the kinetic enolate, right? And so obviously you can't tell the difference here because there's only one hydrogen, but these are kinetic conditions. We generate the kinetic enolate, and the enolate, remember, has two resonance structures. One of the resonance structures puts the negative charge on carbon, on the alpha carbon. The other resonance structure puts that negative charge on what? On the oxygen atom, right, of the carbonyl. However, it's the carbon atom that always behaves, I shouldn't say always, that most likely behaves as the nucleophile under these reactions. And so the nucleophile can then attack the electrophile, in this case just some type of alkyl halide. It can be a primary alkyl bromide, a primary alkyl chloride, or a primary alkyl iodide. Okay? Primary is typically the one that works really well. Secondary alkyl halides can do SN2, but they can also do E2 eliminations, and you have to worry about that. And tertiary alkyl halides, we have a problem because they don't behave as electrophiles, right? They just undergo elimination. So we're really limited for the most part to primary or methyl alkyl halides. And so now we can make the new carbon-carbon bond. And lo and behold, you now know almost all of the carbon-carbon bond-forming reactions that I know. Okay, so through an SN2 reaction, we can make that carbon-carbon bond pretty easily. So here's an actual example. Here we're taking acetone, LDA, THF, minus 78 degrees. We drip in the acetone, we generate the enolate. That enolate then reacts with the methyl bromide, and we form the new carbon-carbon bond. Here we have a ketone. Again, it's a symmetrical ketone, so it doesn't really matter which hydrogen we take. LDA, THF, minus 78, we get the enolate. That then reacts with allyl chloride. It is a primary alkyl chloride, but it's called allyl chloride because the chlorine's on the allylic position, and we make the new carbon-carbon bond. And so in doing so, we actually generate a new carbon-carbon bond. We now have a ketone, and we also have a double bond. We're building up molecular complexity. We now have multiple functional groups. Then in a subsequent step, we can do more things with. Okay? Now I want you all to think about something here real quick. Let me just do it up here on this board, so we'll just black out the screen. Let's suppose that Logan takes this ketone, LDA, minus 78 degrees Celsius, THF, and he generates the enolate at low temperature. And he reacts this with allyl chloride, where the allylic carbon has been labeled, and I'm going to put a star there. And it has been labeled with C13. So carbon-13, it's just an isotope, right? It's an NMR active isotope that we can see really easy in the NMR. What will be the products that he gets when he goes and runs his NMR? What will he see? Will he see just one C13 peak for that carbon, or will he see two? Think about the mechanism. How would you draw the mechanism for this? Okay. Where? Which one's that? Okay, so that can happen, right? And if that's the case, that would be the carbon, right? And he would go run the NMR, carbon 13, and he would see that one big C13 peak because it's in there 100%, and he should only see one if that's the mechanism, right? However, he actually sees two NMR peaks for C13 that are almost equal intensity. What's the other product? We haven't covered this at all, so if you're struggling to figure it out, that's fine. That's what I want you to do.
Does the pi bond move to a more substituted?
Not to a more substituted position, but the pi bond does move. How? No. It is an electrophilic carbonyl, but no, it doesn't do that. Can I? Is that the only electrophilic carbon? It turns out it is not, because it's allylic. This carbon is also electrophilic, because I can attack this carbon, that pi bond will move, and that chlorine will leave, which is called a conjugate addition, which we're going to learn in the next chapter, but this is a perfect opportunity to introduce it. And so the other product is that. And so he sees two C13 peaks in the NMR, because enolates will do the typical addition, but they can also do what's called conjugate addition, and we're going to learn about that. Okay? And so this is an electrophilic carbon, and so is this in these types of systems. Okay? And so we can push the arrows in a way that gives us both products. Does that make sense? So when we are doing these alkylations, quite frequently we generate new stereocenters. So in the experiment where we take cyclohexanone, LDA-THF, and then we react it with ethyl iodide, we make a new carbon-carbon bond, but we also generate a new stereogenic center in the process. There are four things around this carbon. What are they? Why is that a stereogenic center? I have a carbonyl, I have an ethyl group, I have this part of the ring, and I have a hydrogen that's not shown. When you do this reaction, however, you're going to get a mixture of enantiomers, and what's going to be the ratio? It's going to be 50-50. And why is it going to be 50-50? That's right. The enolate itself is trigonal planar. And so if the electrophile comes in from the top, there's no difference than it coming in from the bottom. There's no reason why it should prefer one over the other. And so statistically, we will end up with a 50-50 ratio, and we call that a racemic mixture. That's exactly right. So we generate a stereocenter, but it is in racemic form. Now, there is a lot of work that's going on about how to generate these enolates or enolate equivalents that actually won't give you racemic mixtures. For just because of time, we're not going to go over the stork-enamine synthesis in this class, but you need to read it. It's in the book. It's in this chapter. And the enamine actually looks like an enolate electronically. And you can use chiral amines to make those enamines. And so the top face and the bottom face are no longer equivalent. And you can actually end up generating your stereo centers in non-racemic form. Ideally, you would hope you would just get one. But quite frequently, we get mixtures, but they're not racemic. Okay, because, again, the difference between the top and the bottom is real. One is usually more sterically hindered than the other. And so you can control stereochemistry through things like the Stork enamine synthesis. You need to know the name of that reaction. You need to know what it does. You have all the tools to figure it out. So it's in the book. You need to follow that. So if we look at an unsymmetrical ketone, we learned last time that we can generate both enolates. We can either generate kinetic enolates or we can generate thermodynamic enolates. And so here we have this unsymmetrical ketone, has 2 alpha carbons. We're reacting LDA THF minus 78 degrees. This generates the kinetic enolate, right? Why do those conditions generate the kinetic enolate?
Because they're closer in space.
What do you mean by that?
Like, when it's cold, they don't move around a lot so that they can. So they just attack at the closest side.
That's true.
The kinetic is always formed first.
The kinetic is always formed first. That's true. What else?
LDA is soluble in THF.
LDA is soluble in THF. You're all saying the right things. Let's finish it out. What else? Why THF? It's polar aprotic, but why does that matter? Everything is soluble in it, but if I use a polar protic solvent, even if everything's soluble in it, it won't give me the thermodynamic, or it won't give me the kinetic enolate. What is it about being polar and aprotic? The leveling effect, that's right. So if I had actually done this reaction in alcohol, which is a polar protic solvent, right, what would happen? The alcohol would react with the LDN. I'd actually have alkoxide, which is a weaker base, which would promote the thermodynamic enolate, okay? So it's very, very important that you all keep this together, okay? So we've got our kinetic enolate now. We keep it really cold. And while it's really cold, we add iodomethane, and we can then make this 2,6-dimethylcyclohexanone, which is symmetrical, okay? We can do the exact same reaction, well, in terms of the reagents. So again, starting off with this 2-methylcyclohexanone. But now we're using, what kind of base are we using? It's an alkoxide. This is sodium ethoxide, right? And it's, you make this in ethanol. So what's our conditions? They're basic conditions, but what kind of, is it stronger? Is it as strong as LDA? Is it weaker? It's weaker, right? So we're going to generate our thermodynamic enolate, but this is kind of misleading. I don't know why they did this in the book. This is really an equilibrium, right? Because the pKa of this is not great enough to completely deprotonate my ketone, right? About how much of the ketone would we have deprotonated here? Way too high.
20%.
What's the pKa of a ketone, approximately? 19 to 20. What's the pKa of an alcohol? 16, right? All right, so the pKa of our base is less than the pKa of our acid. So is that going to lie to the right or to the left? It's going to lie to the left. So again, if we know that it's going to lie to the left, let's try to predict a number here. Give me a better range. 10% is starting to be realistic. But that would be if we used a stronger base like potassium tertbutoxide. For this, we're talking about generating less than 1% of the enolate. Okay? And since we always have the acid around and the base, these are going to equilibrate, and that's why we get the thermodynamic enolate. Once we have the thermodynamic enolate, however, it will react with iodomethane, and it will put the make the new carbon-carbon bond, and so we end up with 2,2-dimethylcyclohexanone. And so how is this product different from this product? How would you describe them? Okay, it is. The second product is not symmetrical. That's true. How else would you describe them? If you could only use a couple words. Okay, I'll give you that. One's more sterically hindered than the other, but that's not really where I'm going. Okay. Not really. I'd say they're constitutional isomers of one another, right? They have the same molecular formula, but one has different connectivity than the other, right? Here, the two methyl groups are on the same carbon. Here, they're on different carbons, although their molecular formulas are identical. So they are constitutional isomers of one another, okay? This has real-world uses, the chemistry that we're talking about. Tamoxifen. If you've ever known anybody who has suffered from breast cancer, they may have been treated with tamoxifen. It's a very potent breast cancer treatment. And it is made with nothing more than sophomore level organic chemistry. They start off with this ketone. Okay, you've got these two aromatic rings. One has an ether, one has a bromine. We don't need to talk too much about why that is. How did they make this? What reaction did they use to make this? They used Friedel-Crafts acylation. That's right. They took an acid chloride from this part of the molecule, and then they took that, mixed them together with aluminum trichloride, and they did a Friedel-Crafts acylation. Y'all learned about that. Works really well. They used sodium hydride, which is a good base, right? What's the pKa? About 35, 36. Yeah, pretty good, right? It can only generate one enolate because there's only one alpha carbon with hydrogens. So it can only generate one enolate. However, sodium hydride prefers to form what kind of enolate if it has a choice between thermodynamic and kinetic? It generates thermodynamic because it's not soluble, right? It's not soluble in THF. But it has no other choice other than this one, so it generates this enolate. They simply then react this with iodoethane. What kind of reaction is that? It's an SN2 reaction. Yep, plain old-fashioned SN2 reaction. You get the new carbon-carbon bond that you need. Notice now we've got the ethyl group here. Now all they do is do some additional chemistry that we're not going to spend a whole lot of time to talk about. But nonetheless, you all can do all of it, and you end up with tamoxifen. And it turns out that you have to have the Z isomer to have the beneficial properties of it. That is a very simple molecule. I don't know if this one is a billion-dollar drug, but it's probably pretty close. And it's made with nothing more than reactions that you all have been exposed to. SN2 reactions, Friedel-Crafts acylations, enolate generation, alkylations, right? And if you think about it, how do you go from here to here? What would we need to add? Let's ignore this at the moment. But what would we need to add in this region? We might want to add a Grignard, right? We notice that there's another benzene ring that's in the product, right? And it looks to be like it's on this carbon to me, right? So what could I do? I could take phenyl Grignard, the Grignard that you all generated in lab, add it to that, and what would the product be? An alcohol. What kind of alcohol? It would be a tertiary alcohol. So we would have a new carbon benzene bond here, right? We would have a tertiary alcohol, and then how can I go from that to this double bond? Elimination of what? Water. And what reagent would I use to do that? I would just use a dehydrating acid, right. And what were those? Sulfuric acid is the go-to, but there were some others. Paratoluene sulfonic acid, phosphoric acid, we learned about all of those. You now have just created the core of tamoxifen, again, using nothing more than the reactions that you all have learned, right? And then you got to figure out how to take that off and put this on. That's not too hard. You just treat this with acid, and you can cleave an ether, if you recall, and then you can do an alkylation of the alkoxide with some sort of electrophile that puts this on, and then you have to remove that bromine, okay? And we can do that by converting it into a Grignard and then just dumping it into water if we wanted to, just reduce it off. So all of the, you've learned all the reactions. You could go into industry today and work for them making this kind of stuff. You have the knowledge to do that kind of thing. And that's pretty cool, right? Let's talk about some additional enolate chemistry that we can work with. Let's talk about the malonic ester synthesis. Malonic esters are a special class of what we call diesters or malonates. And so if you look in the red here, you can see that the alpha carbon is alpha not only to one carbonyl, but to two of them. So what do we expect for these hydrogens? Are they more acidic than a typical ester or less acidic? They're more acidic. They're substantially more acidic. Their pKa is 12, 13-ish. So all of a sudden, I can completely deprotonate them with something like sodium methoxide or sodium methoxide pretty easily, okay? And I can take these things and I can deprotonate them. I can put alkyl groups on them, and then I can generate new carboxylic acids. Again, I told you we were going to learn a lot of ways to make a carboxylic acid, and this malonic ester synthesis is one way to do that. So let's look at the example. How do I go from a diacid or a diester to a carboxylic acid, a single just carboxylic acid, or an acetic acid derivative, if you will? It's actually pretty easy. If you take an ester and you saponify it, remember we talked about saponification a little bit, right? That's the hydrolysis of an ester, getting rid of the OR group and replacing it with OH. There are two ways you can do that. You can do it under basic conditions, which is actually called saponification, but you can also do it under acidic conditions, okay, which is just hydrolysis of the diester. So when we take these malonate diesters and we heat them up in acid, we actually get a malonic acid, or so-called beta diacid. And these things are pretty stable unless you continue to heat them. And they will actually decompose under heat to lose carbon dioxide and give an enol, which tautomerizes to the carboxylic acid. And so it turns out that this is actually a pretty convenient way to make new substituted carboxylic acids through what we call the malonic ester synthesis. So let's look at some actual examples. How much time we got left? Oh, we got plenty of time. We got lots of time for examples. That's good. Now, in my laboratory, we do the malonic ester synthesis all the time. It is a staple of the research that we do. And we start off with what's called diethylmalonate. So it's a diester. We can deprotonate this very, very easily. In my lab, we do this in a little overkill. We always like to use sodium hydride. It's my favorite base in the world. It's just so convenient. Produces very few byproducts. The only byproduct you really get is hydrogen gas. That deprotonates just through acid-base chemistry. I know the reaction is going because I see hydrogen bubbles. I do this in the hood without any flames around because I can get a fire, right? That's the only thing I really got to be careful about. I now have a good nucleophile. I will take this and react that with some alkyl halide. Let's just use iodomethane. That's my favorite alkylating agent. What kind of reaction occurs now? We just do an SN2 reaction. And in doing so, we generate a new carbon-carbon bond. Yields for this reaction are nearly quantitative, almost 100%. Usually they're a little lower than 100% because my students have a habit of dropping a little bit on their way to getting things all cleaned up. I mean, you know, you have a few drips that spill here and there, right? It happens, right? But the cool thing about this is I still have an acidic hydrogen there, don't I? I can do this exactly again. I can take this, treat it with sodium hydride, and then I can follow it with, let's say, iodoethane, and now I can make a second carbon bond. So there's the methyl group and there's an ethyl group. I just made another carbon-carbon bond. And now I can heat this up in acid. Remember, the triangle means heat. And I'm going to get an intermediate that I won't be able to isolate. Because that's a beta diacid. And under heat, they like to eliminate what? Not water. Say it again, please. Carbon dioxide, right? So we're going to lose carbon dioxide, and we're going to get that carboxylic acid as our product. The yield, again, is very good. We can then do other things with that acid. We can convert it into an acid chloride and use it as an electrophile in whatever reaction we want. We can reduce the carboxylic acid to an alcohol and use that for whatever we want. Right? We can do all kinds of things with carboxylic acids, as we've learned. I've generated a new stereocenter. Is it racemic or not? It is absolutely racemic. There's no reason why it shouldn't be. I didn't start with any chiral centers, so it should be a racemic mixture. So I'll end up with a mixture of both enantiomers, and we have a new carboxylic acid. And just for your information, this chemistry is the chemistry we never want in my lab. And so we never want it to decarboxylate. We actually want to take the diesters and make other things with them. But I actually have had undergraduate students come into the lab and work, and they get in a hurry, and they work their reaction up, and they go put it on the rotary evaporator to remove the solvent, and they turn the water bath up to like 100 degrees. And they got in a hurry, and then they go get an NMR of their product, and they go, uh-oh, that's not what I wanted. It's because it decarboxylated on them. So sometimes patience saves you a lot of time in the long run. So using the malonic ester synthesis, let me see, how do I draw this? Let's do it like this. Figure out for me, using the malonic ester synthesis, how you can make that carboxylic acid. Work with your partner. Take a minute or two.